Thank you. So good afternoon, everyone. My name is Yue Li. I'm a co-founder, CTO of Members. So we are still a very young startup based in the Bay Area, focused on providing big memories for high performance computing. Today I'm very glad to come here to share with you all the experts on our use cases on genomics. So first of all, what is our motivation? So our motivation basically comes from the simple facts that today's computing problems basically requires more and more memory. And running out of memories become a very common errors you see in your computing tasks. So for example, the latest machine learning model, the GPT-3, for natural language processing. So that has 175 billion parameters. So if you want to use this kind of models, very powerful model for the genomics, you might need a huge amount of memory to actually store the model itself in the memory so that it can compute. So also, the de novo genome assembly pipelines, basically, we got this data from the 10x Genomics that requires more than 512 gigabyte RAM to compute for some non-human data sets. And in our own use case studies, we'll show you the metal genome assembler, Matt Hitmer, developed by the Berkeley, uses more than 4 terabytes of memories for some wastewater data sets. Okay. So basically, memory is the key to the compute because it's actually using more memory, you end up using less storage IOs and less network IO, less distributed, right? So that leads to higher performance. And also with more memory, it computes faster, so faster to the results, and also allows you to fit larger problems into a single machine so they can solve bigger challenges. So however, there's a big problem with DRAM is that DRAM is actually, as you experience, it's very small, right? So only today, the common servers have, maybe 100 gigabyte of DRAM capacity. And so they are very small. And also they are very expensive as well. Especially today, there's a chip shortage, so make the price even higher. So there's basically in today's computer infrastructure, you can see there's a huge gap between the memory and the storage. The DRAM is very fast, but very, very expensive and very small. And storage is still not fast enough. It's large, but it's very cheap. So if you run out of DRAM, you end up doing more IOs and will actually make your performance suffer, or you will run out of memory, which will crash your workloads. So in the recent years, memory development, so we identified actually there is a potential candidate that can fill the gap between the DRAM and SSD storage, which is the persistent memory. So that we actually, our product is focusing on. So here I'm holding on is the persistent memory. Actually, it's a real person. It looks like the normal DRAM DIMMs, but it goes to the DRAM DIMM slots as this one. But it has a huge capacity. So each DIMM, this single DIMM I'm holding, actually can hold 512 gigabyte memory capacity. So if you insert all this into your server, your server will be able to have up to 4 terabyte per CPU socket. So for two CPU socket, you will be able to have up to 8 terabyte of memory in the server. So you can compute large problems. So it's much less costly. It's about 1/4 to one third of the price of DRAM. So it's much cheaper. And also the performance-wise, it's a trade-off. So it's a bit slower than DRAM. It's about 3 to 4 times slower than DRAM, but still much faster, at least 10 times faster than the storage. And most importantly, it's persistent, meaning that if you have power failure, your result can still actually be held in the memory and can recover. So with this kind of memory, of course, there will be more this kind of memory coming up in the next few years. And with this kind of memory, we imagine there will be a software-defined memory solution where you have a DRAM, a PMAM, you have the closest CPU, the CPU cache. So that basically give you, in our vision, we want to give you infinite memory so that you can actually solve the biggest problem you have. So more concretely, so what we did first is we implemented a memory tiering software that is able to combine the DRAM capacity and the PMAM capacity together to give you a huge memory pool in a single server so that you can compute large problems. So this tiered memory, basically, we put hot page. We also not only provide you a large memory, we also monitor your memory access patterns. So we put meaning that we put hard data in the DRAM so that you can get the most of the performance of DRAM, And then we put also the code pages in the PMEM so that you can save the cost. And also it allows you to configure basically very flexible DRAM PMEM ratios. For example, you have an application that really requires performance, you can let the application to run only in DRAM. But if you have an application, you don't care how long it will take, but you just hope that it's large enough to finish your work, you can actually let this application to run only on PMEM. Or you can do something in between, right? And then all these kind of ratios are basically can be done per application, and can also be dynamically updated. So if you are not happy with it, you can actually tune the ratio in real time without restarting your applications. In the future, what we are building actually it will be enable you to actually borrow the memory from other machines as well. Say that you have a machine that is very fast, has lots of memory there, but it's not very busy. So you can actually borrow those memory from those machines and to your small memory machines to help you to finish the job. So here's basically the estimated memory cost if you use the memory tiering solutions. Essentially, the data is basically calculated based on the recent Dell price server pricing obtained this month. You can see that essentially per gigabyte cost-wise, the obtained PMEM, which is the second row, is basically about 1/4 of the price of the DRAM price there, right? So with that $1,000, you can get a 128 gigabyte memory. But if you want DRAM, you can only get 64 for $2,000, right? And here I plotted basically with different DRAM PMEM ratio, you can achieve different kind of memory cost savings as well. So for example, if you want to achieve 1/4 ratio, which is 0.25, then you will be able to save about 150% of the memory cost. So I just want to briefly mention a use case here. So we also have a talk on Thursday, but we conducted a collaboration with the Berkeley, with John is here, basically to do the metagenome assembly to run on this big memory machine. And the motivation is very simple. If you look at this real data sets, so these are terabases, right? So these terabases can convert to terabytes in memory if you want to feed them into the memory. And if you want to assemble these data, basically this requires huge amount of memory. So we tested all these popular metal genome assemblers on the big memory machines we have. And here basically shows that all these are feasible and they give the different kind of trade-offs. So I will not go into the details. We'll talk more on Thursday. So also, we also recognize that if you use more and more memories in your compute, that actually might present new challenges also. So we're not only trying to give you the big memory, we're also trying to provide you other data services that can help you to better leverage the big memory. So for instance, if your compute holds a huge states in the memory, let's say you have a huge intermediate results holding in the memory for analysis, right? So it will take you very long time to actually write them to the slow storage because the NFS or other storages are very slow. And also, if you want to restart from that state you saved, it also takes a long time because you have to actually ship them. You have to deserialize them and ship them to the memory from the remote storage, which is also very slow. Think about moving terabytes of data between the remote storage and the local DRAM servers, right? So it's also it's long time to save to this, long time to recover. And also, if you really want to make a copy inside the memory, it's also very expensive, right? If you have terabytes of data. So to do that, to solve these problems, we also developed another tool, essentially, we call it in-memory checkpointing technology, or in-memory snapshot, that allows you to actually persist your data, take a photo or take a snapshot of your data instantaneously inside the memory, so that you can actually recover. If you have a failure, power loss or failure of your workload, you can actually recover your compute state instantaneously within the memory without actually using the disk storage. Think about this really as an in-memory checkpointing, transparent checkpointing for your high-performance workloads. And of course, with this in-memory snapshot, you can not only recover, you can also actually clone the memory. We have actually snapshot technology that allows you to clone the memory into multiple copies. By doing the memory sharing technology, you don't actually consume extra memory. You can actually still share the same piece of memory, but clone into multiple processes to compute in parallel. Or one process used for debugging, the other one used for production, and so on and so forth. And all this can be done without actually modifying your applications. So this is just to give you more details here. Essentially, you can ignore the picture here, but basically the snapshotting allows you to do achieve instantaneous checkpointing for your applications without modifying your application. So it does not move the data from memory to storage. It actually persists your data right inside the memory. And we can do that because the persistent memory actually provides persistence and also provides large capacity also. And these snapshots can be cloned into multiple copies. Let's say you have application here, you take a snapshot. With snapshot, you can actually clone multiple copies of the same application. They will behave exactly the same. So, but you can ask each application to do different tasks. And we can also replicate the snapshot from one memory in one machine to the other machine. And you can also then restore the application inside that machine. Say that you're submitting this job to some queue, right? The queue has to terminate your task. Then what you can do is you can take a snapshot and you can actually replicate the snapshot to another instance or submit it to another queue and recover there and continue workload from there. And also, of course, we also support, you can export to the external storage. Let's say you want to move your workload from on-prem to the cloud, you can do that as well. So I want to just mention a few quick use cases of this snapshot feature or checkpointing features. One interesting use case is that allows you to save the cost of using cloud. Say that you want to use the cloud, AWS, or Google Cloud, or Azure to do your high performance workloads, right? And those are typically, if you use lots of memory, it's very expensive. So one way to do the cost saving is to use so-called a spot instance, right? So all these clouds, they have different names. So basically, the spot instance is kind of like the unused resources offered by the cloud, which provides a very deep discount. Typically, it's 3 to 10x cheaper than the normal instance you get. You get the same configuration, but it's just much cheaper. But there's always a trade-off. It's cheaper because it's unstable. This means that the cloud can reclaim this spot instance anytime. And they will only give you, a few minutes notifications. For Amazon, it's I think 2 minutes, and Azure is like 30 seconds. So they will reclaim the instance. Your workload will be gone in 2 minutes. That's the notification you get. So it offers you can see the price here. The cost saving is huge, right? So it's very attractive. But with this kind of limitation, it's very hard to use them directly for your complex, long-running big memory workloads, because once it starts reclaiming and you didn't save the states, and it's gone, right? So essentially what we did is, this is from a real customer case study. We run this so-called alternative splicing analysis called Splatter. And this application is very long running. And we run this on basically on-demand Amazon AWS instance also, and run on Spot instance. Except that for the Spot instance, we enable our snapshot capability. So essentially, we periodically take the snapshot of the application status. And then once we detect that the cloud is reclaiming the Spot instance, we'll automatically resume the workload from the snapshot to make sure it can finish. So at the end, if you use the on-demand, very expensive instance, it takes 17 days to finish. And use Spot instance with our basic fault tolerant services, it takes about 19 days to finish. But if you compare the cost, we only cost about $300. And if you use the on-demand, it's about $1,800, which is much more expensive, right? So it's about 83% cost savings if you use checkpointing with Spot instances. And we also have on-prem use cases. Also, this is actually for a Chinese company, genome analysis company. They are doing single-cell RNA sequencing analysis. So as you may be familiar, they have lots of, this analysis essentially has lots of pipeline, has a big pipeline with lots of stages there. Some is cleaning up the data, some trying to do some projections, some trying to do the visualization, and so on and so forth. And they have the requirement, essentially, they have to save all the intermediate data at each stage for reproducibility, and also for kind of the parameter tuning, because there are some clustering stage here that's trying to basically do the kind of like they want to do the parameter tuning, so to basically to create the best clustering results. So we notice that this kind of workload has three properties. So this is a basic in R, the SURAT package. And essentially, we saw that, first of all, it's very memory hungry. It easily used up more than 500 gigabyte memory. And also it's storage bottleneck, because every time it saves the intermediate results, it takes a very long time to actually finish. And it's, of course, it's long running, and it's also very iterative. The scientist has to keep on restoring from storage and trying to change the parameter over and over, trying to find the best results. So essentially, conventionally, it looks like this, right? You have different, blue box basically marks different stages of the analysis, and orange basically is they always have the save and write and read, basically to save the intermediate result to the storage, which takes actually, we typically takes thousands of seconds actually to finish. They have to take a coffee and they come back. So here is essentially what and during the parameter tuning, you have to restart from the reloading stage, then trying to change the parameter and run again, which is very time consuming. So we work with them, essentially we change their R script and to embed our snapshot tools here. So essentially now you can actually remove the save and the reading, but replace them with a snapshot command that we did here, which takes only about 1 second to persist your in-memory states. And when you want to do the parameter tuning, you can actually restore the snapshot, which you actually recover your workload in 1 second. And you can try a different parameter tuning. So this basically greatly improved their productivities and the performance. At the end, the baseline takes about almost close to 25,000 seconds to finish the whole pipeline. But now we're able to actually eliminate almost all the IOs, and we reduce the running time by 60%. You can see the most of the time we removed is the storage IO time. Now it's much, much faster. And the scientists can actually perform more and more iterations to do the parameter tuning.
2 minutes.
Okay. I think the last use case is very quick. So essentially, this is the cloning. So we have another use case where the scientist is doing another single cell genomics where the stage 1 is basically loading all the data, and stage 2 does actually serial computing because of the limit of R. You cannot parallel compute. But you have to, but different color marks different type of compute based on the same data loaded in stage 1. So this is the conventional way they're doing this. So what the collaboration we did with that is essentially after stage 1, we take a snapshot and we use the cloning, basically by cloning them into 4 processes in parallel, and each process just compute 1 single task. In this case, we parallel the compute and shorten the time from 6 hours, 30 minutes to 4 hours and 11 minutes using our in-memory snapshot capability. And so that's, I think, all the cases I want to discuss here. And finally, we have our presentation with John on Thursday to talk more about the metagenome assembly on big memory. Thank you very much.
I think we have time for 1 or 2 questions.
Yes, please.
One of the popular workflow platform in bioinformatics is NextFlow, and its behavior is that it writes a lot of intermediate data to the disks between the processes, so the NextFlow processes. I was wondering whether this technology would be able to make the NextFlow behave much faster.
Yeah, we actually heard about NextFlow, but we haven't done any integration with that. So we have to take a closer look at the NextFlow, the sample workloads. Yeah. I can.
Thanks.